Good morning, everyone. Nice of you to show up. I think you should be at the beach, but since you're here, let's do this. I'm going to talk a little bit, advertise a project we call Quasars, Probing Quasars, or QPQ, and say a little bit about the transverse proximity effect, which is mainly a work in progress, so not too many results today. I'll show you a figure or two towards the end. I wanted to start, though, with a couple of slides honoring Bill, who is our honoree this week. I showed this slide at the last Joel Fest I attended. It was a talk on galactic winds with Kate Rubin and Dan Kaysen, and we were using iron 2 transitions to study galactic winds. So that's what these are, multiplets of iron. And here's kind of some zoom in of them and their gory detail. And this is just a few of the levels of the tens of thousands of transitions or energy levels that iron 2 has. I have it here for Bill and because he's really one of the few people in the world, when I got excited by iron 2 transitions, that I could actually go into his office and he'd know right away what I was talking about and could provide some physical insight on the spot. And then even in the next day or two, he was already coding up a program to understand the transitions we were observing and trying to understand how we were exciting them and so forth, and actually in the context of gamma ray bursts. So it was really been a pleasure over my 10 years here to have Bill to interact with on all matters. Atomic transitions, I'd say the sessions on the IGM, CGM, whatever, I think Bill probably knows more about that topic, has more physical insight than the rest of us combined. So we should be appreciating that as well. The other slide I put in here for Bill, who appreciates this one? A few of you, yeah, right. When I think of Bill, I think of the back of a blue Volvo. When I would come in late to work or to remotely observe, I pretty much always would see Bill's car parked in front of the dumpster next to ISB, the back of his blue Volvo, making his presence known. Yeah, I'm sure he still comes in late at night. I don't know if he's driving a blue Volvo anymore. In fact, he stopped parking at the dumpster. I think he got tired of the parking tickets. At UC, yes, you can work until your very last day, but they'll never let you park where you want to. And yeah, it's a testimony to his passion and for the science. I think of him and his blue Volvo. Right, so QPQ, with a little bit of emphasis on the transverse TPE, transverse proximity effect, which I appreciate probably most of you have no idea what that is. So let me give quite a few introductory slides. QPQ, it's a project we are using to study quasars and the environment of quasars, primarily through spectroscopy. So here's a quasar spectrum. Perhaps most of you have seen one by now in your careers. Observed wavelength on the x-axis, flux here, roughly a power law. This comes from the Magellan telescope. John O'Mara and Michele in the back there, they took this nice spectrum with a MAGE spectrometer. On top of that, roughly power law spectrum, SED, are these emission lines from hydrogen, Lyman alpha, some silicon, carbon emission as well. You may recognize this, you may not. This is the so-called Lyman alpha force, or it's the intergalactic medium. It's absorption from hydrogen gas primarily in our universe. That lies foreground of that quasar. The aficionados amongst you may have recognized this. This is what we call Lyman limit system, LLS. It's a blob of gas in front of the quasar that's optically thick at the Lyman limit and is absorbing all of the ionizing photons that it's receiving. So that's why the flux goes to zero, or essentially zero, there at that wavelength. Here's the same figure now in rest wavelength. Okay, hydrogen emission, the carbon lines are 1550, and Lyman limits are down around 900 angstroms in the rest frame of the quasar. That's one quasar spectrum. These days you can take thousands and thousands of these. Here's actually a stack of about 100 average in the quasar rest frames. Here's the Lyman alpha emission again, some nitrogen 5 emission, Lyman beta and O6 emission there. This is the Lyman alpha forest when you average it with about 100 different quasar spectra. There's still strong absorption there. You can't really tell unless you're expert in this field, but there's a significant opacity there. It's absorbing quite a few of the photons on average from these quasars. And then here again is where you expect the Lyman limit, and you can see a roll-off, a decline in the flux down there at the Lyman limit. You can actually use that to measure the mean free path of ionizing photons in the universe. That's another talk in its entirety. But you should be impressed that there's photons, there's light being transmitted through there. So quasars emit ionizing photons. Probably most of you knew that, but here's some proof positive of it. On average, quite a few ionizing photons. And then the intergalactic medium absorbs them, but doesn't absorb them all the time. Back to our single quasar, now zoomed in a bit. Here's the forest again, right? Lyman alpha emission of that individual quasar. Here's that Lyman limit system. There's something missing here. I know it's only 9:30, but I'm going to make somebody tell us. What's missing from this spectrum? Lyman beta would be in there. It's a bit absorbed, but it's there. Joel, you're a smart guy. What's missing? Yeah, there's no DLA. But which one is really missing?
Which one?
Which DLA is missing? There's one that's blatantly missing. The one at the quasar and the galaxy hosting the quasar. There's no galaxy. You don't see any sign of the galaxy. That's right. So this Lyman limit system is not occurring at the Lyman limit. It's occurring blueward of it by some tens of angstroms in the rest frame here. So there's no absorption here at Lyman alpha, or essentially none. Certainly no damp Lyman alpha system. And here's the Lyman limit of that quasar. There's no strong opacity there.
There's another massive galaxy on the line of sight.
There must be foreground to it. Yep, many tens of megaparsecs away. Totally unrelated. Yep. So quasars do have affect their environments. You're probably aware of that, but here's proof positive. They've blasted away. This is what you should have seen. This is what you should see if you observe a source at the center of a star-forming galaxy with interstellar medium. This is a gamma ray burst spectrum. And the gamma ray burst affects its very local environment, tens of parsecs, but doesn't affect kiloparsec scales, the interstellar medium. That's what you should be seeing. There's Lyman alpha absorption, okay, from a host galaxy. And here's the Lyman limit of that GRB spectrum. And again, going back to the quasar, we're not seeing anything like that. And that's typical of quasars. There are counterexamples. There are some cases, we call them proximate absorbers, where there is strong absorption at Lyman alpha and a Lyman limit at the Lyman limit. But those are actually quite rare. So that's a proximity effect of sorts. LOS stands for line of sight proximity effect. Quasars do zap their gas locally. For the aficionados, that we know that when we say line of sight proximity effect, we don't really mean affecting the host galaxy. We actually mean affecting gas on large scales. And so I've really zoomed in on this quasar spectrum. And up top, this is observed wavelength. Up top here now, I'm counting megaparsecs, proper megaparsecs away from the quasar itself. As we head to the left, 1 proper, 11, 20, whatever, 30. And this is a bit subtle, this effect. Subtle enough that you may not even believe it when I'm telling you here in a single quasar spectrum. But if you compare the opacity, the average absorption of the IGM away from the quasar, say tens of megaparsecs away, versus the opacity here quite close to the quasar, you may believe when I'm telling you that there's an absence or a decrement, less opacity in close to the quasar, and we attribute that to the radiation field again of the quasar. Not so easy to see in a single spectrum, but if you look at many quasar spectra, it's statistically significant, especially at these redshifts. And the point is that the quasar outshines the extragalactic UV background out to something of order 10 megaparsecs. Actually, it should be 10 megaparsecs squared. OK, so that's the line of sight proximity effect. It's been studied for decades. I'm focusing today on the transverse proximity effect, which you can boil into a question of, do quasars shine in other directions? We know they shine towards us. Do they shine in other directions? And if so, what's the effect on the environment? And so on and so forth. Of course they do. All right, that shouldn't be a surprise to you. So what can you learn from studying this so-called transverse proximity effect? You can get constraints in the quasar lifetime. Unlike the line of sight where the light has to travel to us and through the medium, right? We have a finite travel time in the transverse directions. The quasar's only been shining for 1 million years. Well, it can only affect 1 million light years bubble, essentially, around it, even if it is shining in all directions. Similarly, you can get constraints on the quasar opening angles, which tells us a bit perhaps about the torus and aspects of that of quasar phenomenology. The duty cycle, if they turn on and off, maybe you can see evidence for that. By, again, looking in the transverse direction, not as opposed to the line of sight, or putting the two together. The challenges here, or a challenge in this, is that we have to do this analysis, we have to understand the distribution of gas around quasars. And that's where I've been focusing my attention for the past few years with Joe Hanawi, a major collaborator, and the feedback that quasars impose on those scales. And so we can actually use these types of analyses to study the gas around the galaxies hosting quasars and perhaps gain some insights as well into quasar feedback. This slide is meant to give you a sense of, again, of how you can use transverse proximity effect to study aspects of the quasar phenomenon. The color code here is the opacity of the intergalactic medium, or the transmission really, where 1 is fully transmissive, no absorption from the IGM. Yellow here means about 30% of the flux on average would be absorbed if I ran light through gas at, say, 5 megaparsecs away from a quasar. You all follow that? This here would be 5 megaparsecs away from a quasar in the transverse direction, and the average opacity, if I didn't have a quasar shining, would be of the order of 30% of the light being absorbed. Turn on a quasar and shine it in all directions. You lower the opacity so the color goes to the red, and then you can play around, make the quasar a bit obscure, make it episodic, and you can see that you get different signatures in the opacity of the intergalactic medium. And it's these types of signatures that we're going to be exploring with our experiment. Any questions on that? This is theory. This is make-believe. It's a numerical, a massive dark matter simulation only, with baryons painted on it. And I don't think there's hardly any, in this simulation, I don't think there's any effort to actually model the gas on scales of hundreds of kiloparsecs. In fact, I'm sure there isn't. So to do this experimentally, we use quasar pairs. That's QPQ, quasars probing quasars. And we need quasars that are not physically associated. One is behind the other at many megaparsec separations. We call those projected pairs. Here's an example. This is actually our closest pair that we've discovered over the years. A few arc-second separation, which works out to about 30 kiloparsecs physical at the foreground quasar redshift. So this one, the one with the blue arrow, lies in front of, very far in front of the one with the green. They're not at all associated with each other. And so with our own follow-up efforts, we've discovered and now observed hundreds of these. And you can actually use massive spectroscopic surveys like Sloan and Boss to do this analysis on larger scales where the fibers don't collide. So many hundreds of kiloparsecs. Quasars are hosted by massive galaxies. I'm not going to dwell on this. Just accept it. If you haven't believed that before, you should. Their clustering strength is large. Implies halo masses of a few times 10 to the 12. Quasars shine and perhaps also push gas around. There's feedback processes, so they are affecting their environment on scales of tens, hundreds, who knows how far kiloparsecs. Something to keep in mind as we're studying the gas. As I said, the first papers I've been working on are on the nature of the gas on pretty small scales. We call it the circumgalactic medium. Here is just to give you a sense of the size of the data set. Each letter here is a different quasar pair. This is a radius of 300 proper kiloparsecs. Here's some of the data. And we're studying the foreground quasars, which are marked here at Lyman alpha, absorption by the yellow arrows. Here's our data set out to a megaparsec radius. That's that inner 300 kiloparsec radius. Here's now a megaparsec. You can see we've got about 1,000 quasar pairs to play with on those scales. Here's some results. You'll hear a bit more about this one. Unlike the line of sight where I showed you, there's typically no absorption at the Lyman limit in quasars. When we go in the transverse dimension out to a few hundred kiloparsecs, we see a high opacity, a high fraction of Lyman limits absorption. Roughly 60–70% of the sight lines show strong absorption at H1 Lyman limit out to about 200 kiloparsecs. So completely different than what we're seeing down the barrel, suggesting that the quasars are not shining isotropically or have very short lifetimes. We'll hear more about that, I think, in Michele's talk. We can probe the gas and metals, the circumgalactic medium. I'm not going to talk more about that today, just to say that we can do it. Here's just some of the data. We can probe it in low ionization states, high ionization states of carbon. And along with that gas that I just described, hydrogen gas, we see plenty of metal absorption. These are equivalent widths out to, again, hundreds of kiloparsecs. So there's, around these massive galaxies at redshift 2, we've got a cool, metal-rich, massive circumgalactic medium out to several hundred kiloparsecs. In fact, the circumgalactic medium exceeds anything that we've seen both in the local universe and in the distant universe. This is the strength of absorption. This is equivalent widths. The strength of hydrogen absorption out to 250 kiloparsecs around these quasars. That's basically what I've just shown you, but now in equivalent width. Here are similar measurements, but for Lyman break galaxies. We believe those to be hosted by galaxies that are about several times less mass. They show several times less absorption in neutral hydrogen. These are modern galaxies, L-star galaxies like our Milky Way, observed by Jessica Work, Jason Tomlinson, and myself with the HST. And this is what we see in dwarf galaxies today. And so kind of a sequence and mass of the strength of absorption in the circumgalactic medium around massive galaxies to dwarf galaxies today. Now extending it out to a megaparsec, these are the 1,000, roughly, spectra. Maybe it's actually 500, one by one, shown here, shifted to the rest frame of that foreground quasar. So 0 is where the foreground quasar lies in H1 Lyman alpha. And if you squint, I think you can see that there's excess absorption around that 0 velocity, and perhaps stronger absorption, not perhaps, but definitely stronger absorption as you go in closer, now out to a physical megaparsec. Here it is smooth, and here it is really binned up. This is a map, if you will, of hydrogen absorption around quasars at redshift about 2 out to a physical megaparsec. So very little evidence, in fact, no evidence for the type of proximity effect that we see along the line of sight. I showed you that's a decrease in the H1 opacity. We see an excess of H1 opacity out to a megaparsec and beyond physical around these massive galaxies, which is to zeroth order the prediction of our cold dark matter cosmology. It's just also coupled with the fact that the quasar cannot be shining preferentially in those directions, or even much in those directions. We've been studying the correspondence between these strong absorbers with the quasars themselves. I think I'm just going to skip that slide. It's very interesting. If you're interested in optically thick gas and galaxies and their absorbers and their relationship to galaxies, come talk to me afterwards. This is almost a whole talk in itself. Finishing up with some of our recent work now on the transverse proximity effect. This is where we're headed. QPQ6, that was the analysis out to megaparsec. That'll show up on AstroPH next week. QPQ7 is the corresponding metal line analysis. QPQ8, Marie, you'll have that submitted by the end of the summer, right? Wherever you are, Marie. That's detailed description, analysis of the circumgalactic medium around quasars with a shell level spectroscopy, where you can really look at the abundances and the chemical composition and the ionization state of the gas, the kinematics, how it's moving around, and probe signatures, if there are any, of feedback on those scales. To the transverse proximity effect, we now need to go out yet further. And this is a 3 megaparsec proper radius, which is almost 10 megaparsecs co-moving. And we're just focusing for the transverse proximity effect on hydrogen, on H1 Lyman alpha. So this is a slide which will not appear on Joel's website because it's work in progress and because it's kind of tantalizing to me. I'm plotting the stacked average absorption profiles, or average spectra, let's call it that, at Lyman alpha of the foreground quasars as a function of impact parameter. So this is everything up top. And then this is 140 kiloparsecs, 500. These are proper. A megaparsec, 2 megaparsecs, 3 megaparsecs. You see declining absorption with increasing radius, more or less. But two signatures that I don't really understand, which is partly why you won't see it on the website. This large shift in the absorption, that's the kind of thing you expect for transverse proximity effect. At least it can be interpreted as a transverse proximity effect, where the gas in front of the quasar is preferentially ionized by the quasar, as opposed to and that's just light travel time issues. And then this very weak absorption here, again, only 30 quasars so far, but compared to anywhere else, if there's a signature of the transverse proximity effect, I'm seeing it here in this relatively modest data set. And so we're going to be analyzing these data. This is a subset. These are quasars. The foreground quasars all have more precisely measured redshifts. So really the reason why I really will hedge on any of these results is establishing quasar redshifts, which is necessary to do the stacking and all of the analysis, is difficult. We use magnesium-2 for this data set. There are 3 gentlemen in the back, no, not in the back, in the front, who have been working hard all summer to improve our redshifts. And so here's some of the fruits of their labors. We've been taking near-infrared spectroscopy of as many of these foreground quasars as possible to go after transitions like H-beta. I think that's H-alpha here, even though it's not marked. O3 emission, to really precisely, as best as we can, really precisely measure quasar redshifts, which feeds back into that transverse proximity effect. I'll remind you that an error of 100 kilometers per second, that's 1 megaparsec physical, 1 megaparsec co-moving at these redshifts. And so that can smear out the effects that we're looking for quite rapidly. And so nailing this as best we can is where we've been putting a lot of our efforts. And I think that's about all I had to say. That there's plenty of theory work going on behind the scenes or within the scenes. Sebastiano and Michele, I think we're presenting some of this today. This is a slide that Sebastiano put together of a massive galaxy, massive halo. The gas around it here in total surface density and here in H1. And some of the puzzles that exist here is really this does not explain the data that I've shown you today. You'll hear some more about that, I think, in the talks to come. And I think I'll just leave up a summary slide. Thanks.
So we have time for a few questions. Yeah.
Did you say anything quantitative about spectra or electrons?
Today, no, I will not. At all. Sorry.
If this node up there contradicts cold flow paradigm,
Eh.
that's the wall cycle, could that just be the gas that you're looking at? What about distance from cold flow? Does it cover such a small fraction?
When I say contradicts, yes, we're seeing more absorption than you would naively predict, I believe, from streams of cold gas onto galaxies. So contradicts is probably too strong a word, but let's say cold flow paradigm does not trivially explain the observations.
You see too often or
Too much absorption. Yeah. Yes, Joel.
Joe?
Just on that issue, presumably these are massive galaxies.
Yeah.
Their halos are much more massive than 10 to the 12 solar masses that are redshift that you're observing that.
Yeah.
So cold flows have probably been cut off.
The gas has gotten too hot, indeed.
But more to the point, I think what you're arguing is that there's injection of gas.
There may well need to be.
And of course, we often see strong winds associated with objects like this.
So it's that easy?
Well,
I should stop worrying?
It's not a huge surprise.
Winds may well have to play a major role here.
That's usually what you see, so.
And we're seeing metals in the gas,
Well,
so.
suppose the gas reaches the galaxy, but now there may be huge winds driving off everything. But I guess the point is that you'll have enough data that you can really characterize the situation.
Absolutely. Yeah, and that gas better be coming out of the galaxy's cold.
Right.
That's not so easy to do to hundreds of kiloparsecs.
How are you going to have winds driving out all the gas isotropically that there aren't things on the moon isotropically? I mean, the winds are always going to take the path of least resistance out of this galaxy. It's very difficult to actually remove the gas that way.
I agree.
Anything else? If not, let's